Hey everyone, welcome back. Today is day 6 of my 30-day FAANG grind, and I'm solving 6 to 10 LeetCode problems daily, sharing with all of you on YouTube through my explanatory videos. I'm Divya, by the way. I've interned at Massachusetts Institute of Technology, where my area of focus was on statistics and machine learning. Currently, I rank at top 0.3 on LeetCode, and I love solving LeetCode problems. In the past, we have already covered sliding windows, two pointers, prefix and suffix based problems. We also tackled problems based on strings and problems based on stacks. Today, it is all about binary search, which is one of the most powerful and versatile techniques in coding interviews. We will go beyond just finding a target and expect to solve problems based on rotated arrays, lower and upper bounds space, and binary search on answers, and much more. Before I begin, if this content helps you, please smash that like button, hit subscribe, and share it with your friend, which will mean a lot to me. So let's go. So the problem that we are tackling today is LeetCode 704, and it is the foundation problem for binary search as the title suggests. It is an easy level labeled problem, but it is a really fascinating problem, and we'll dig deep into this and build a really good foundation to solve all the upcoming binary search problems of varying difficulties. Okay. So in this problem, we have been given an array which is sorted in nature, and it can contain elements which can lie on the left of zero or on the right of zero. Means they can either be positive or negative. And we have to scan the array and find the target value. If the target exists within that array, then we have to return the index at which the target exists. But if the target do not exist, in that case, we will just return -1. One thing to note is that we cannot simply do a linear scan. Why? Because the question asks us to complete this solution in logarithm times span, okay? We'll come to that. These are the constraints of the problem. Let us go to our dashboard and we will try to investigate and find an optimal solution for this problem. Cool. So we have been given an array nums and we have been given a target and we have been asked, hey, does the target exist in nums? If it does, please return the index where the target exists. If we do not, then please return -1, which will imply the target do not exist. What is the brute force approach? The brute force approach would be, hey, let us start from the left hand and we'll go on as long as it is possible for us until we find the target in the array. We'll iterate over every single element and we'll compare it with the target. If that element is equivalent to the target, then we will return the index where that element is present, and that will be our answer. And this technique is bounded within linear time complexity, okay? But we can do much better. Why? We can do much better because one of our scientists, they invented this technique called as binary search, which applies on sorted array. And fortunately, this array is sorted. So our job and our time complexity will become much, much, much better. It will not be bounded within linear. Instead, it will be bounded within log scale. Okay. And we'll see what does that even mean. Cool. So before I begin, my bad. Okay. So before I begin, let us one of the recipe for binary search is that there are few elements that we need to maintain. There are few pointers that we need to maintain. And those pointers are very essential to the core of the binary search. Those two pointers are initially pointed towards both of the ends of the array. Okay. So the pointer pointing to the left end, I will call it L or left pointer, and pointer pointing to the right end, I will call it R or right pointer. Now, what does these two pointers imply? These two pointers imply, hey, this is our search space bounded within these regions, okay? And we cannot go to the left of this or we cannot go to the right of this. We'll just stay within this space, okay? This is our universal space. Cool. Okay, but how will that help us? Cool. So to answer that question, since we have two boundaries, our first objective will be to find the mid of it. And The mid of it, I'm assuming it will point to this. Okay. Now, the mid of it can point to that as well. But again, for the assumption case, I'm just assuming that it is pointing to 5. Okay. As in this part is the middle part. Cool. Now, when we look at the middle part, which will be represented by a variable called as mid, we ask ourselves a question. Hey, the value that is present in the middle part, is it greater than the target value? Or is it smaller than the target value? Or is it equivalent to the target value? And depending upon these three questions, either of these pointers or these pointers or the mid pointer will answer our questions, these three questions. Okay, cool. And we'll see how. For example, I will show you the code. Uh, cool. So in this case, we see that 5, it is smaller than 9. What does that mean? It means a few things. It means, hey, since we know that our array was already sorted and we encountered a value from left to right, we encountered a value 5, which is smaller than our given target 9. What does it tell us? It tells us, hey, every single value before 5 must be smaller because it is sorted in ascending order, in increasing order. Okay. If every value before 5 is smaller than 5 itself, then that means they must also be smaller than 9. Why? Because 5 is already smaller than 9. Okay. But if every value greater than 5 or on the right of 5 is greater than 5, it implies there is a chance for us that we might find our target value on the right side of 5. Why? Because every value that comes to the right of 5 can be around the scope of this value, okay? Or the magnitude of this value. Cool. So in this case, we see that 5 is smaller. So what do? We move the pointer of the lower value to mid plus 1. In this case, left, it will move to mid plus 1, which should be over here. Okay, L plus 1 comes over there. Let me erase this thing. And right now, L will point to this part. Okay, and R is pointing to that part itself. Okay, now when we take mid once again, when we compute the mid of these two boundary, mid will point to this part. Okay, and when mid points to that part, we again ask these three questions. Hey, is the mid greater? Is it smaller? Or is it equivalent? We see that if mid points to this index, mid is equivalent to the target. So in that case, what do? We return the mid value of the index, which is this part. Okay. So as we can see in these three bullet points, mid and target compares. Cool. Every time we make a comparison by standing on the mid to our given target, left pointer, it will move if mid is smaller than target, which was obvious. 5 is here, which is the mid. The left pointer moved. Why? Because 5, which is the mid, was smaller than 9. That is why left pointer moved over here. Right pointer, it will move if mid is greater than target. In some cases, for an example, let me show you a 1. Let let this be 10 and let this be 11. Suppose our target is 1, okay? And mid will point to this part. Good. This part, we know that this is the mid part, okay? And we know mid is greater than target, which is 1. So every element following mid will always be greater than 1 because we know that if anything that comes after mid is greater than mid and mid is already greater than target. So in that case, what do we do? We will shift our right pointer to mid minus 1, which will place right pointer to exactly where L is. And in that case, we will compute the mid and we'll get this value as the mid, which is equivalent to the target. And then we'll return whatever the index of this place is. In this case, 0 index, okay? Cool. So that was all there was to the explanation of this video. Let us walk through the code pretty quickly. We have two different pointers, left to the left hand, right to the right hand. We run a loop such that those two pointers stay within the bound of each other. Then we compute the mid value, and then we ask these three questions. And according to those questions, we make a movement. If mid value, if it is equivalent to target, we simply return mid because that is the index that we need. If it is less than target mid, we move the load to the right part. If mid is greater than the target, we move the right part to the mid minus 1 part. And once this entire loop is exhausted, we come out of that and return minus 1. which imply that the target was not found within the array scope, and left and right pointer, they overlapped each other. Not just overlapped, they crossed each other's boundary, okay? So this loop will break when left will become greater than right, okay? And that is what will happen at one point if we do not find the value. Time complexity in this case is logarithmic, and the space complexity is of order of n, which is constant because we are just declaring variables, okay? Now, let us go to the LeetCode dashboard and we'll try to submit the solution and see how it all goes. I'm at the dashboard. I have already submitted a solution for this problem, so I'll just copy and paste it. And where is the problem I got? It should be here, I think. Okay. Oops, not again. Okay, let me type it pretty quickly. Left is this, length of nums minus one, while low is less than high, our mid will be low plus high by 2. If nums of mid, if this is including target, in that case I will just return mid value. And if nums of mid, whatever the value is, if it is greater than target, then we know that target might lie on the left part. In that case, high will become mid minus one. As if nums of mid, if it is less than target, possibility is that target might lie on the right side. In that case, low pointer will move and it will become mid plus one. And once all of that is exhausted, we'll return minus one. And this should just work fine. And target is not defined. Okay, this is the typo there. TARGET. Okay. And as you can see, it, oops, I think I mistyped once again over there. The target. And yeah, as you can see, it ran. Okay. So yeah, that was all there was to this problem. But before I wrap it up, I just want to show you something. The time complexity thing. Okay. We knew that this problem, it could be approached using two methods: linear, which means we have to scan the entire array to find the value. The other was doing the binary search, where at each point we were bifurcating the array into two, which means binary, into two different parts. Okay. And then we're making a scan based on the mid value. Okay. Good. So this is the time complexity graph that I plotted for you. Again, the number of data point, as you can see over here, it is just 10 or yeah, 10. And I chose such a low data point because I wanted to show you the curvature that is getting formed over here. Okay. You can see this green plot, right? That is the solution for our binary search problem, the time complexity for the binary search problem. And the red one is the linear scan problem, okay, which was a brute force for this problem, okay. Now, as you can see, this graph, as it proceeds further and further, the gap between the red line and the green line, it increases. Notice one thing, that currently this graph, it is just for 10 data points, okay, or 9 data points, correct? But what if, and this is the gap, this is the actual gap that you can see over here, okay? But what will happen if this gap or the data points, if it increases, how will our computer, deal with that thing? So let me just increase this value to million. I think we are at 1 million data points, and let me run this thing, okay? And when we run this thing, it will take some time. Okay, so see, the gap is enormous, is it not? From the origin point on the left, where both the green line and the red line extends forward, you can see as we move right and right forward, we see that the gap keeps on increasing, and it should strike us. It should strike us because it should show us the power of logarithmic scale, the power of logarithmic time complexity. Okay, and yeah, I just wanted to yeah, show you this thing that by the graph. I hope you enjoyed this thing. If you did, please leave a like, and if you have any questions, please ask me in the comment section, and I will help you out. Bye bye.